first. So I think you have the recordings of earlier classes. All the 4 classes I have taken. I have shared the link for the recorded videos through your class representative. So I think you have that. And if you have any question on those lectures, you can ask me right now at the beginning of this class. Then we can continue with this. If you have any query. Anybody has any query?
Sir,
Yes.
sir, is the small R1 represent the sir is the small R1 represent the resistance of the wire and the coil, primary coil?
Yes. This is the winding resistance. For the winding 1 or coil 1, R1, small r1 represents the
Okay, sir.
resistance of that, which will get rho L by A by that formula. Where L is the length of the coil and the area is the cross-sectional area of the wire used for the coil. And rho is the resistivity of the material you have used for that winding. Generally copper. Anything else? So let me ask you some question. That here in this circuit, that you can see directly on the whiteboard. So here we have used some notations like capital I1, capital IC, capital IM, etc. And some other variables are also there at the right, where I have written small I1, small I1 prime, small IM. So can you tell me what is the difference?
Sir, small I1 are the instantaneous values, whereas the capital letters are either the RMS values or the vector values. Like.
Okay. Can you mute yourself or phone? Some noise is coming. Or phone Chakraborty? Okay.
Oh, okay, sir. I have unmuted.
Okay, so I think you have understood the difference between the small letters variable and capital letters variable. Now the next question is, so that means the time, that instantaneous values are basically the time variable thing, isn't it? Okay. Now, then what are the different types of inductance we get in case of transformer?
The mutual inductance, self-inductance.
Okay. So is it mutual inductance or something else?
Sir, one is
Mutual.
magnetizing inductance and another is leakage inductance.
So the reactance, no? Leakage reactance or magnetizing reactance, no?
Can you tell me the difference? Do you know the difference? Now, what is the unit of inductance?
Sir, Henry.
Whenever there is a inductance in a AC circuit, it will provide a reactance, the resistance, which is called
Yes. Louder, please.
So you asked that.
Sir,
So you
Henry.
asked that what was the difference between that inductance and the reactance.
Yeah.
So in this case, means whenever there is a inductance in the AC circuit, there will be a resistance which it will create, and the total resistance, the equivalent resistance of the entire circuit will give the reactance.
No, it's not like that. Now you just tell me the
Like
unit.
reactance is the property, but
I'm asking the unit only. Now you can tell that. What is the unit of inductance?
So the unit of the inductance is Henry,
Henry and
and
ohm.
reactance.
Reactance is
Ohm.
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 Henry.
Okay, so inductance is Henry and reactance is ohm. Both of the property, isn't it?
Yes, sir.
Okay, so both are the property of the coil. Now,
Sir, reactance, sir.
yes,
Hello.
yes.
Sir, I'm saying, sir, in the reactance and impedance are same.
In other part of this
Sir,
subject,
can you hear me?
yes. Can you hear me?
Yes, sir. Yes, sir.
In other part of the subject, how many classes you have attended? The part which is being taken by Professor Mita Dotto. Other part of the same subject. How many classes you have attended so far?
4 lectures, I think.
4 lectures. So what are the things she has already discussed?
She's teaching AC right now.
AC right now.
So have you come across this? Have you come across these terms? Inductance, reactance, etc.
Yes, sir.
Yes, sir.
Okay. Now you see, let me tell you this because this is not my part of this discussion. Still, I have to discuss a little bit, otherwise, you will not understand this. Okay, so inductance is basically the property of a coil, isn't it? That I have already mentioned in some earlier classes that inductance is a property of a coil. Now, what is that property? The property says that if there is any change in current, you can underline the term change because that is the most important one. If there is any change in the current flowing through that coil, then there is a voltage induced in the opposition of this current, and that you know that very well that is the voltage which is induced equals to L di dt. So that means inductance is basically doesn't allow the change in current. Inductance is such a property for which a coil doesn't change, doesn't allow any change in current. Okay. So this expression I think is well-known expression for inductance, isn't it? V equals to L di dt. Rather we can write it VL. Suppose we have an inductor, okay, and suppose some current is flowing through it, that can be inductance current, if there is any change in this IL value, then a voltage will be induced in opposite direction, and that voltage will be VL, where VL is represented by this equation. I have to write all these small letters because they are the function of time. So both this VL and IL, they are function of time. Okay, is that clear? So this is the definition of the property which is called inductance. Now, so there is a transformation. I think you haven't come across that, which is called the Laplace transformation. Have you come across this term, Laplace transformation?
No.
Not yet?
Sir, yes, in the sound,
Yes, sir. Yes, sir.
in sound, where
Yes,
we
sir.
speed of
Yes,
sound.
sir.
No, it's not a speed of sound. It's basically an integration.
Yes,
No, sir.
yes,
No,
sir.
sir.
Sir,
Basically an
sir,
integration.
is it the integration?
Yes.
Sir, is it the integration 0 to infinity f of t to the power minus ht dt?
Yes. Okay.
Sir, is it the one that is used to like convert like the integration of like a real say variable to like a complex variable?
So this is the definition which I have just written on the whiteboard. So this is the definition of Laplace transformation. Now, as per this definition, in brief, we can say if we have a function of time like small ft, if we have a function of time small ft, what does Laplace transformation do? It converts this time domain function into another variable s domain function. So that's all a Laplace transformation does. It converts a time domain function into an s domain function. Now s, actually s is a complex variable. Time is a real variable, but s is a complex variable. Generally we call it complex frequency, and therefore the unit we mentioned here, that is radian per second. So both the values sigma and j omega is radian per second. Okay. Now when we take the Laplace transformation of any derivative, it becomes a function of s. So suppose VL was the function of t. When we go for the Laplace transformation, it becomes V of L. Now L is completely a constant number. So therefore, there will be no change of L. But in the right hand side, you have a derivative. When you have a derivative, a term you will get is S into the Laplace transformed current, that is IL function of S. Okay, so here, so I think you will be learning all these things in the other part, or in maybe in the mathematics classes. So here we have assumed initial conditions 0. Okay. So that means this same equation, after Laplace transformation, we have this expression where A is equals to sigma plus j omega. Okay. So that means previously the relation between this VL and IL was an inductance L with the derivative sign. Now you have no derivative sign. What you have? You have only an S term. And S is multiplied with L and there is no derivative. So that is the advantage of Laplace transformation. So another advantage of Laplace transformation is that it converts any differential equation to algebraic equation like this one. So this equation becomes an algebraic equation. No longer it is a differential equation. Okay, and this power of the S, here is the power of the S is 1. Now this power of the S depends on the order of the derivative. Here what is the order of the derivative? Is the first order derivative. So therefore we have S to the power 1. Okay, so this is how from the derivative we get the S term out. Okay, now when you will
So
study
that
the
means that this Laplace transformation is basically.
yes,
So can we say that this Laplace transformation is a kind of gamma function?
না গামা ফাংশনে তো f of t
no no
always
no
x power something থাকে।
হ্যাঁ
no
ওটাতে
that is different.
x to the power minus m থাকে।
That is different. So it's a Laplace transformation is different. Okay, now depending on this S value, as I have already written that sigma plus j omega. Okay, now actually when we'll go for the solution of any variable, so we'll have two states. One is called the transient state, another is called the steady state. Transient state and steady state, two states are there where this sigma is present only in the transient state. Okay, and in the steady state it becomes 0. In steady state it becomes 0. In steady state, that means in steady state we have only S equals to j omega. And if we represent the same equation, instead of S, if we write j omega, then the equation becomes, it's not a function of, no longer a function of S. Just a minute. Somehow it has been stuck. Okay. So it becomes a function of j omega. Because S becomes j omega. Okay. Now, what we can write here, that we have an element where we have the voltage across it is VL and current through it is IL. Okay, and this VL by IL, this term is j omega L or JXL. This XL is called the reactance. Okay, which is having the unit of ohm. So this is how we got the reactance part from this inductance. So that means in a nutshell, we can say the reactance is basically the product of angular frequency of the supply and the inductance value of the coil. Reactance is the product of angular frequency of the supply and the inductance value of the coil or winding. So that is the difference between inductance and reactance. Okay, so inductance is a property of the coil. Reactance is also a property of that coil, but it is a derived property. It depends on omega also. That means a same inductor can give different inductance value. Okay, suppose in our country we have 50 hertz frequency. We'll get for same inductance, we'll get some XL value. But in some other countries, like European countries, they use 60 hertz supply. For that, they would get a different reactance value. Okay, suppose in aircraft, they use 400 hertz supply in most of the aircraft. Okay, so you will get a different inductance, reactance value for the same inductance. So that is the difference. Okay, so inductance is the basic property of the coil, but reactance is a derived one. And it also depends on the frequency. Is it clear? So anyway,
Yes, sir.
Sir, I had a doubt in the core loss component of the current.
yes,
Sir, you said that the core loss component IC and RC, the resistance, are both fictitious quantities that we have created to explain the core loss of the due to the magnetic flux in the core.
yes,
But sir, here IC is flowing through R1 in the circuit, and R1 is a real resistance. So it will have a loss of IC square R1. I
yes.
don't quite understand what type of loss this is.
That is a purely ohmic loss. Okay, now
But
suppose,
sir, IC is,
bolo.
sir, like maybe I've misunderstood, but I thought IC was only present to produce the core loss IC square RC.
Yes.
And like
Actually,
when you said it's fictitious and it's also
IC is a part of your no load current, isn't it? IC is a part of no load current. Okay, now this IC, when it flows through RC, we have the core loss. Okay, but this total I naught will also flow through the series branches, which are R1 and leakage inductance LL1. So when this part IC will also flow through this R1, there will be a copper loss, simple ohmic loss. So that will be there. Okay, but when it flows only through the resistance this RC, then we'll have the purely core loss component. Is it okay?
so, sir, then IC is actually being considered a part of the current that is flowing, but RC is the only fictitious part. Like RC
Yes.
cannot be, like RC is not actually existing there, but we are quantifying it to explain the loss.
Yes. So everything is like that only. If I ask you what is the resistance, can you see the resistance? Is the resistance is like this? Not that. It's just a representation. Actually, you are getting some ohmic loss. For that, you are considering some resistance and through which some current is flowing and some loss is getting occurred. Okay. Now, in the last class, I told you that this circuit is okay. Only the thing is that I1 is shown in the circuit, but in which branch that I1 would flow. So that has not been drawn in this circuit. Okay, so only the voltage is given, that is E1 is shown in the circuit, isn't it? Now, what type of element should be there across these two terminal? What type of component can be shown? Because we don't have any more resistance or inductance to be shown, isn't it? So all the inductance and resistance we have already shown in this circuit. So what else should be there in the circuit which will connect these two terminal and through which this I1 current will flow? Remember, this I1 is basically called the load component of primary current. Load component of primary current. And I naught is called the no load component of primary current. So what branch we should, or what element we should draw between these marked terminals so that through which we can show I1 current is flowing. Okay. Now, if we can remember that what is E1? E1 by N1 or E1 by E2 is equal to N1 by N2. Can you remember this expression? This is a very basic expression of voltage voltage ratio or trans ratio, isn't it? We all have this expression. Now, if we write that E1, what is E1? E1 is N1 by N2 into E2. Now, what is this N1 by N2? It's just a ratio. It doesn't have any unit. It's just a number, isn't it? So that means we can write some value, suppose alpha into E2. Okay, so that means this E1 is basically depends on E2, isn't it? That E1 is
Sir,
dependent.
is it the dependent voltage source?
Yes, it's a dependent voltage source.
Okay, sir.
Okay, but if we show that, we can show that, but what else we can show there? So this E1 we can show there. Okay, so let me draw first the other part of the circuit, then I will come back to this. So I think you have understood this. So we can show some dependent voltage source over there. So before that, we should go to the other part of the circuit. So for this coil 2 or secondary, uh, what we can draw for it, for the secondary, as we can draw something for primary, what we can draw for the secondary? Now secondary or the coil 2 is a different coil. Okay, it would also have some resistance, let's say R2, because coil 2 is a different coil, its resistance will also be different, and it will also offer some self inductance or leakage inductance. So that means we can write that LL2. Okay, but what is the equation from which we can get all this? Have we written this equation? like the equation, the KVL, KCL we have written for the primary. Have you written any equation for the secondary? Okay, for the secondary, what is the voltage? For coil 2, what is the voltage? Can anybody tell me?
Sir, E2.
So
No,
for
E2.
okay,
E2.
so
E2.
for coil 2, the source is E2.
Sorry, E2.
For coil 2, the source voltage is E2. Yes. Okay. And if there is some current flowing, so current will flow through which elements? Through R2 and through L2. Isn't it? So let me write first in time in instantaneous value, then we'll go for the RMS or other thing. Okay, so E2 equals to I2 R2 plus LL2 di2 dt. Okay, so what else will be in this equation? There will be another voltage V2 which is available at the output of this secondary coil. That means, suppose if we can remember the secondary that we have drawn like this, where the voltage induced was E2, and here you have connected some load, okay, through which the voltage which will get, that is V2. So V2 is called the terminal voltage. Okay, and so therefore we can draw this equation like this: E2, and here we have the load through which this I2 current is flowing, and across this load we'll get some voltage drop, that is V2. Is this clear?
Yes, sir.
V2 টার্মটা কি করে আরেকবার একটু বলবেন?
হ্যাঁ বলো, V2 টার্মটা কি করে এলো?
মানে I2 R2 আর LI2 DI2 DT টা তো বুঝলে, মানে V2 টার্মটা।
Okay, so let me
ওটা
explain
তো
that.
অ্যাক্রস লোড নাকি?
Let me explain that. বুঝতে পেরেছি সমস্যাটা তোমাদের কোথায়। Suppose you have a battery. Have you seen battery? Suppose it's a 1.5 volt battery. The pencil batteries like AA, AAA batteries, 1.5 volt batteries. So if we measure the voltage by some voltmeter, how much voltage you will get when it's a new battery? Can anybody tell me? Yes?
Sir, less than 1.5 volt.
No, if it is a new fresh new
So less
battery,
than
you will get,
1.5.
if it's a new fresh battery, you will get 1.5 volt only.
1.5 only.
Because that is the rated voltage, isn't it? Now what you have done, you have connected a very teeny lamp, okay, with this battery, and the lamp starts glowing. Now if we measure the voltage, can you tell me how much voltage you will get?
তো দ্যাট ভ্যালু মাইনাস ওই ভোল্টেজ ড্রপ যেটা হবে বাল্বের ওখানে ওই
No, no,
1.5 ভোল্টই হয়।
তো সেমই থাকবে।
হ্যাঁ ও সোর্স তো ওটা সোর্স তো সেমই থাকবে।
No, sir. Due to
Yes.
current in the circuit and the loss in the internal resistance, the voltage meter across the battery will be less than 1.5 volt.
মানে ইন্টারনাল রেজিস্ট্যান্স থাকলে ড্রপ হবে।
If we consider the internal resistance, there will be some drop.
Okay, so that means you are saying which internal resistance? Internal
স্যার যদি ইন্টারনাল রেজিস্ট্যান্স যদি থাকতোই তাহলে তো সেটা প্রথমবারই সেটা নিউলি ব্যাটারি তো পাওয়া যেত সেটা।
কেন পাওয়া
না
যাবে?
প্রথমবারে দিলে তো কারেন্ট তো জিরো হয়ে যাবে, ভোল্টমিটারের রেজিস্ট্যান্স ইনফাইনাইট,
Correct.
সে কারণে কারেন্ট জিরো, সেই
So
কারণে
voltmeter offers very
তাও ঠিক,
high impedance. So therefore, when initially you have measured that with the voltmeter, it will read 1.5 volt only, because here ideally the current drawn by this voltmeter, ideally, practically it's in the order of milliampere or so, but ideally it should be zero. So you will read, it will read 1.5 volt only. But once you will get some load connected with this battery, and when the battery load is drawing some current through it, the battery has its own internal resistance. Any battery will have its own internal resistance. Okay, then the voltage that you will get in this case will be less than these volts, and that is due to the internal resistance of the battery. Okay, so that means this voltage you can say your open circuit voltage E2, which you are getting here, and this voltage you are getting as a V2, and this is the drop. So here also in our transformer or in the coil in the secondary, you have the open circuit voltage E2. When the current will be drawn by this load, there will be a voltage drop due to the internal resistance or internal impedance of the coil. As it's an AC application, will get internal impedance. We should mention the term internal impedance, not internal resistance. In case of DC batteries, we can use the term resistance, but in case of AC application, we have to use the term internal impedance. So due to this internal impedance drop, the voltage will be different. The voltage will no longer be E2, it will be V2, which is E2 minus I2R2 minus LDIdt. Now is it clear?
Yes,
The
sir.
significance of V2? Okay. So
Yes, sir, it's clear.
I think you have understood this term. Now, so here you see this I1. What is this I1? I1, how this I1 is formed?
So to balance the MMF which was caused in the secondary.
Okay.
Yes, sir.
So that means we can write also one thing, that I1 N1 equals to I2 N2, isn't it? And this I1, what we can write? Can't we write this? One by alpha into I2, isn't it? So that means I1 is basically a current control current source, and that we can show over here. And the value is 1 by alpha I2. Okay. And what is E2? E2 is 1 by alpha E1. So that we can write over here. So that means Here we have a voltage control voltage source. So E2 is completely dependent on E1. So therefore it's a voltage control voltage source. So have you understood these two circuits? So one for the primary, another for the secondary. You just see these two circuits carefully. Okay. I think you have understood this. So if you have understood, then we'll proceed with this. So you have understood these two circuits. One circuit is representing the primary winding and another circuit is representing the secondary winding. Remember, the primary and secondary winding of a transformer is not an not a constant one. That means the primary coil, which you are saying primary, it can be also the secondary. That depends on the source connected. The coil at which you have connected the source is called the primary, and the coil at which you have connected the load is called the secondary. Now you can change the side, then the names will be different. Okay, so that means the primary and secondary coil are not constant for a transformer. Okay. Now for this, the circuits I have drawn here, one for the primary, another for the secondary. It is basically the equivalent circuit of primary and equivalent circuit of secondary. Okay. Now equivalent circuit of transformer is different. Equivalent circuit of a transformer is only one circuit. It's not two circuits. In some books you will find there are two circuits. But remember, the equivalent circuit of a transformer means it's a single circuit. It's a single circuit which will represent both the primary and secondary. But it will be a single circuit. Now you know that transformer is not a single circuit, not a single electrical circuit. It's a two electrical circuits. But when we'll go for the the equivalent circuit of the transformer, we have to make only one. So how to make one circuit out of these two circuits? So that I will discuss. The problem is clear. So we have two circuits. From these two circuits, we have to make one. Is that clear point? Now, what is the problem to connect these two circuits? The problem you just see that here for the primary, at the output you have E1 voltage, and here at the input you have E2 voltage. That means these two voltages are not same. Not only that, here in the primary the output current is I1, but here in the input you have I2 current. So they are also not same. So that is the problem of joining these two circuits together. Neither the voltage nor the current are same for these two circuits. If they were same, then only we can connect these two circuits together. So how to make them same? Now, the equation which we have written for the secondary, if we write once again, so it will be E2, okay, Am I right? E2 equals to, what is that equation? E2 equals to I2 R2. But now I will write all this in capital letters, and then it will be reactance. So all are in capital letters. So you try to understand how I am writing this from this equation. Next day I will ask you this, how we are getting this equation from this equation. The equation, the instantaneous value you have understood. From this equation, how we are getting this equation. Anyway, so this is the equation, you can say, at steady state. Okay, so this equation you can modify in this way. Suppose if we multiply both sides by n1 by n2. Again it has hanged. So I am multiplying both the side by n1 by n2. Okay, so we have multiplied both the sides by n1 n2. Can anybody tell me what will be the left hand side?
E1.
Sir, E1.
E1, sir.
So it becomes E1. Okay, sorry. So it becomes E1. Now if we write the I2 in terms of I1, it will be N1 by N2 into I1. Isn't it? So that you can check from the previous expressions. So that means we can write this is N1 by N2 whole square into I1 into R1 into I1 plus N1 by N2 whole square. J is the imaginary number, root over -1 into I1. And here only N1 by N2, not whole square, into V2.
স্যার এটা R2 হবে না?
Yes. It will be R2 only. Okay, so
N1 into whole square.
yes.
Second term J into N1 into whole square.
Yes, yes. The second term also will be whole square. Just we are writing the equation in terms of E1 and I1. Okay. Now you see what is the unit of N1 by N2 whole square?
So it doesn't have a unit.
So what is the dimension of N1?
No unit.
N1 by N2 whole square into R2.
Sir,
Resistance.
resistance ohm.
Is another resistance, isn't it? So that means it's another resistance which we can write R2 prime. This is also another reactance which we can write XL2 prime. And this we can write another voltage which is V2 prime. Okay. And from this equation, so this is the derived equation. Only we did some mathematical operations on the existing equation. So according to this equation, the new circuit is similar, but their values are different. This becomes R2 prime. This becomes XL2 prime. This becomes E1. And this becomes, across the load, it becomes V2 prime, isn't it? Now you just see these two circuits. So circuits of the modified secondary and circuits of the primary. You see at the output you have E1. Now in the modified circuit we have E1 at the input. At the output you have the current I1. In the primary here also current which will flow through these elements is I1 because this clear from this I1. Now we can, that means now we can connect these two circuits, this modified secondary circuit and existing primary circuit. Okay, isn't it? And how it will look like? It will look like this. This was the original primary parameters. This was I1 prime. This was I naught. This is IC. This is the magnetizing current. This is okay. So we can also write LL1, LL2, or you can write XL2. Here also you can write LM, or in steady state parameter you can write XM. Okay, so this all becomes the referred value. They are not actual value, they are called the referred value. So this becomes the exact equivalent circuit of a transformer, where we are representing both the coils, both the primary and secondary coils. You have parameter for the primary coil like R1, XL1, RC, XM, and the parameter for the secondary as well, which are R2 prime, XL2 prime. Is it clear? So this is called the exact equivalent circuit of a transformer. So this circuit is a single circuit where we can represent both the parameters of primary as well as secondary. Is it clear?
Yes, sir.
So any doubt? Anybody has any doubt? Okay.
Sir, can you tell where will we practice questions on these concepts?
From where you can practice the questions? Numerical problems.
Yes, sir.
For numerical problems, I suggested one book by P.S. Bimra. You have lots of problem worked out there, and also some problem in exercise. So if you want to practice numerical problems, you can consult that book. Number of
Like for
problems.
these concepts, what chapter do we have to read, sir?
Transformer only. At the very
Okay, sir.
beginning, you have a chapter called transformers. Okay.
Okay, sir.
In that chapter itself, you will get all these ideas. Okay. Anything else? Okay. Now, what we'll do? Uh, we'll discuss the phasor diagram. Have you studied phasor?
Yes, sir.
Okay. Suppose, can we brief now how many equations we have studied so far? We have two KVL equation, two KCL equation. So for primary, we have the KVL equation B1, I1R1, okay. What else? 1. This is equation number 1. Now equation number 2, that is I2, rather E2 minus I2R2 So this is the KVL equation 2. Now we have two KCL equations. And I naught equals to plus IC. So these four equations are very important to derive the equivalent circuit as well as for phasor diagram. Now other relations also we have which connects the primary and secondary, and they are E1 by E2 equals to N1 by N2 and MMF balance equation. So these two equations are also very important to understand the magnetic coupling, and also the fundamental equation, that is EMF per turn. So we have studied all these equations. By all these equation, we can solve any problem. We can we can derive any phasor diagram or any equivalent circuit for transformers. Okay. So I think you have understood all this equation. No more explanation is required. Now we can proceed for the phasor diagram. Now we'll take first the equation number 2. Because if you want to understand this practical scenario, then if we have a transformer, okay, so here you have some incoming line and some outgoing line. So this is your transformer. You have some input voltage, we have some output voltage. And why this transformer is required? To cater some load, I2. Okay, now this I2 is not decided by the transformer. How much current will flow, that completely determined by the user itself. Okay, power utility like CSC or ACDCL will not decide how much current will be drawn by a consumer. Consumer himself or herself will decide how much current he or she will draw. Okay, so that means that is our independent variable, that is I2. I2 is the independent variable, and as it is a phasor, it has two things. One is the magnitude, another is the phase. Okay, now this phase this phase will be measured with whom? For I2 the reference phasor is V2. Okay, and that is our starting point. Suppose V2 is the reference phasor. Okay, and what is the I2? I2 may be leading, may be lagging, or maybe unity power factor. If it is a lagging load, then I2 will be like this, and theta 2 will be drawn like this. Is that point clear? Okay, so why we are starting from this side? Because we have several equations just now we have written. We have two KVL, two KCL equation, two equation relating their magnetic circuits, and one very basic equation for EMF per turn. But why we are starting from equation 2? Because in equation 2 we have the independent variable, that is I2. And the magnitude and the phase angle of I2 is completely determined by the type of the load, okay, switched on by the consumer. Suppose you as a consumer, you have switched on light, okay, so some fluorescent lamp or some LED lamp you have connected, or you can connect some refrigerator, you can connect some fan, you can connect some air conditioner. So that depends on you. Now, depending on the type of thing you are connecting, type of appliances you are connecting, that phase angle and the value of the current will be determined. Okay, suppose you are connecting some LED lamp, so you will get some I2, will get some theta 2. But if you connect some air conditioner, so you'll get much higher current, that you all know, that much higher current it will draw. Not only that, this phase angle will be compared to the LED one, the phase angle will be also higher, because the air conditioner is basically there you have a motor, and the motor consists of several coils inside it. We all know. If we don't know the exact the thing which is inside AC, but we can say that it has a motor, and motor consists of several coils. And if there are coils means it's an inductance. But in LED lamp we have very few inductance. So if we have large inductances in some device, we'll get the theta high. Okay, and as it's an inductance, so therefore the angle will be lagging. For all inductances, the angles are generally lagging. And in our household applications, generally we use some coils in most of the devices. We don't use capacitors. Mostly we use the coils or the appliances in which we have a lots of coil. So therefore, in our household application, generally we consume lagging power factor load. Lagging power factor load, or in other words, it is called inductive load. Inductive load. Inductive load is not, doesn't means it's completely inductive. It means inductance plus resistance, which is called the inductive load. So in our household application, we generally consume inductive load or lagging power factor. So therefore, we have started with this assumption that suppose some inductive load is taken by the consumer and the value of the load current is I2, and it uh, makes an angle theta 2 with the reference voltage V2. So that is our starting point. Now what you have to do, you have to make the phasor, the all the voltage component complete. Now here we have, what are the components we have? We have V2, I2R2, I2XL2 and E2. Okay, so that means if we add V2 plus I2R2 plus JI2XL2, then only we can get E2, isn't it? Now can you tell me what will be the phase angle of I2R2? It's very important to understand the phasor diagrams. If we have I2 phase is like this,
Opposite to V2.
opposite of V2.
V2.
Why? I'm asking this I2R2.
It will be in phase.
It will be in phase with
Sir,
what?
it will.
Same
Sir, it will.
phase.
I2.
Sir, in phase with I2.
In phase with I2, because R2 is just a number. It's not a vector or phasor, isn't it? R2 just a number. So it will give some scalar multiplication with I2. So therefore, it will be in phase. In phase mean in parallel also you can draw it. So you can draw it in parallel with I2. But it will be scaled by R2, so you can write. So it's a different unit, it's a voltage unit, though I2 is the current, but I2R2 is the voltage. So therefore, you have to draw I2R2 like this. So this is one voltage component. The next voltage component we have is JI2 XL2. Now what do you mean by this J? J is root over of -1. In phasor diagram, what do you mean by J? J means 90 degree leading. When we are
Sir,
multiplying
rotation.
it means it's 90 degree leading.
Rotation.
Follow? So that means it will create some 90 degree with this I2 phasor. Suppose this is I2 phasor, it will create some 90 degree. Now 90 degree from this point, 90 degree you can write in this side, 90 degree you can draw this side. As it leads the I2, lead means anti-clockwise direction, it will create the angle. So it will create the angle in anti-clockwise direction, it will rotate. So therefore, this will be your JI2 XL2 term. So this J means 90 degrees. So J
স্যার এটা
means,
আরেকবার বোঝাবেন স্যার?
বলো কি বোঝাবো? Why J means 90 degree?
স্যার এই যে এটা মানে স্যার উপরে কেন হলো, নিচেও তো হতে পারতো, মানে
90 degree leading. J means 90
এটা
degree.
কেন
অ্যান্টি ক্লকওয়াইজ হিসেবে ঘোরায় তো।
J means 90 degree leading, and concept is our
কিন্তু মাইনাস যে
concept
I2 XL2 আছে তো
মাইনাস যে আছে তো ওটা তো 90 ডিগ্রি ল্যাগিং হওয়া উচিত।
হ্যাঁ হ্যাঁ আমারও তো
Remember
তাই
this
মনে হয়।
expression, this V2 plus I2R2 plus, you can just see the equation once more. It is V2 plus
স্যার
I2R2
প্লাস থাকলে তো লিডিং করবে, কিন্তু যদি মাইনাস থাকতো
minus
তাহলে তো
lag.
ল্যাগ করতো।
If it was minus, then it
হ্যাঁ
would
সেটাই।
lag. But here we have plus only. As we have added the I2R2, so we have to add this Gi2XL2. Okay, and the resultant of these three is E2. So that means this resultant will get like this. This will be the E2. Is it clear? So this is how we can add three vectors to get the resultant E2. Is it clear? You just check it whether it is clear or not. So J means 90 degree leading. Okay. How we are getting this 90 degree leading? You can explain this very in a easy way, that basically this J is coming from inductance, isn't it? So L di dt. Okay, now this I is basically Im sin omega t. When we'll get the derivative, so it will be cos omega t, isn't it? So that means it was sine, but when you are taking the derivative, it becomes cos. So cos means it's 90 degree leading, isn't it? When it becomes cos, cos leads 90 degree, leads by 90 degree. So therefore, when we are getting this J term, basically we are leading the reference by 90 degree. So therefore, J means 90 degree leading. Okay. So the next one is E1. So if we know the phasor of E2, we can also know the phasor of E1, because E1 and E2 are in same phase. Because you know this E1 by or E1 by N1 equals to E2 by N2. And N1 and N2 is not vectors, are not vectors, they are simply numbers. So therefore E1 and E2 are in same phase, only their values are different. Okay. So yeah, if it is a step up transformer, E1 will be more, E1 will be less than E2, and if it is a step down transformer, then E1 will be more than E2. Okay, so let us take a step up transformer. So we can write E1 like this. They will be same phase, only their values will be different. Okay, is that clear? Next, we have to draw the phasor of the magnetizing current and flux. As we know, actually we will use all this equation we have we have written before. So what is E1? E1 is 4.44 F phi n into N1. So that is regarding the value. But from this we cannot evaluate the phasor relation. For phasor relation, we have to go for this equation. E1 equals to minus n d phi dt. Now, when we are taking this, forget about this sign. When you are getting this derivative, how much phase lead or lag will get? We have just explained here. When we are going for derivative, what will be the phase angle, lead or lag? Some scientists. Huh? So derivative means 90 degree lead or lag. Suppose we have a phasor like this. Suppose we have a phi like this. So when we will derivative, we take the derivative, what will be the phasor? It will be leading or lagging?
So leading by
Sir,
90
leading
degree.
by
Lead by 90 degree.
So it should lead. So derivative means it should lead by 90 degree. But as we have negative sign, basically it will lag by 90 degree, isn't it? Is that clear?
Yes, sir.
So therefore, here we have to draw the phi m in this direction, because E1 should lag phi m by 90 degree. Here also E1 is lagging phi m by 90 degree. So therefore, it will be 90 degree lagging. And who generates this phi m? Phi m is basically generated by MMF. Which MMF? I1, IM, N1. This MMF generates this. So that means phase angle of the phasor of IM and phi m will be same. So that means you will get IM in the same phase. Is it clear now?
Yes, sir.
Okay. So I think I should not. I should stop here because it's not a complete phasor diagram. The rest of the phasor diagram we'll discuss in the next class. And if you have any question, you can ask. In the meantime, let me take the attendance. Okay. So I have taken the attendance from the screenshot. So if you have any question, you can ask.
Sir, one of the student has been disconnected just now. Roll number 1129.
Okay, so I am just taking his attendance. 1129.
29.
Okay.
Yes, sir. Shubham Shaha.
Okay. Any question you have? You want